Okay, great. Hello, everyone. Thank you for coming to this session. I'm going to be talking about artificial intelligence. Peter Coffey is a very difficult guy to follow generally, but what he was talking about is relevant to what I'm talking about today. So I'm talking about artificial intelligence in the enterprise. My name is Dave Carroll, developer evangelist at Salesforce. One of the cool things about my job is I've been at it for 13 years and I've seen a lot of changes in Salesforce and I've seen a lot of changes in technology, and I think artificial intelligence is one that we should be paying attention to, hence the reason why I chose this particular topic. How many of you guys have been to Dreamforce or anywhere else that Salesforce is presenting? I almost wish that we could just fingerprint everyone into the room and say, okay, they've already seen the forward-looking statement slide. But this is it. I'm obligated to read this slide to you. Instead, we'll just say, don't make any buying decisions unless it's a generally available product that you're thinking about. And I need some water available. Okay, so how many of you guys have a definition in your mind of artificial intelligence? Not everyone. Okay, that's interesting. I think, after the HAL 9000 and all that, people would kind of have at least an idea. And so I wanted to start kind of with the basics. Start easy, because we're going to get a little bit more complicated as we go in here. One of the things I want to do with this talk is not talk about necessarily only talk about Einstein or Salesforce products, but try to give you a layman's understanding of the machine learning behind artificial intelligence. Now, I'm not a data scientist. I've actually just kind of really immersed myself in the last 5 weeks into learning about machine learning and artificial intelligence, and this is what you'll see is the result of it. Also, I've got a whole bookmark folder full of reference material that I've been digging up, so if you're further interested after this session, let me know and I can pass that on to you. Okay, so the obvious artificial, that's something that's made by humans. It doesn't occur in nature, of course, like a computer. And then intelligence is really where we want to spend our time today. And that's the acquisition and the application of knowledge resulting in skills. And so it's important to kind of keep that distinction that there's the acquisition of knowledge, but then the application of knowledge is the important part and part of what Peter was talking about today. And artificial intelligence is all around us at this point in time. These are some examples. Spam detection, that's artificial intelligence. You get to teach the spam detecting machine by reporting spam when you see it. I think that I've had the same email address ever since Gmail started, and my inbox would be all spam if it wasn't for their spam detection algorithms. Self-driving cars. This is a fantastic example of artificial intelligence. Just because of the sheer number of things, the sheer number of decisions that are made moment by moment for the car. And all of these decisions are being made by a machine based on sensory input. Search engine result optimization. This is AI that's been in use since the mid-90s. So Alta Vista, who remembers Alta Vista, right? If you go to altavista.com, you'll end up at yahoo.com now. But Alta Vista was applying artificial intelligence to the search result optimization. And I think without that, Google would be pretty useless. How many of you do a search on Google and get past the first page, go to the second page? But on rare occasions, right? I mean, it's very rare. So it actually does a pretty good job of figuring out your past history, probably knows a little bit more about you than that, and then presenting the appropriate results. Image searching. Has anybody tried the Google image search? It's okay. I mean, you're not going to find your doppelganger, for instance. You may not have one, but it works pretty well. This is AI. language translation. So Peter Coffey stole my thunder on this one. This is a great story about DeepMind, a group inside of Google, that they were applying the problem of language translation to their new DeepMind system. What, excuse me, what Peter didn't mention, though, is that optimizations and improvements in language translation were happening every year. You know, the team wasn't sitting on their hands, and they were getting like 0.2% increase in efficiency and accuracy, which was pretty good. That's actually, you know, you go 0.2%, but that's a high value. Once they applied the DeepMind neural network self-taught algorithm, it was a 4% increase in the accuracy of the language translation. And the other interesting part about this story is they rolled it out without telling anybody. So there were no press releases or anything like that. They said, well, let's see if anybody notices. And so about midsummer, they just turned it on for a subset of their users just to see if anybody would notice. And almost immediately, people are like, did they swap out their search engine or their translation engine? So that was a pretty big win. So there's some other things, video gameplay. This one's, I don't know, I don't play video games, but I guess it moves characters around in relation to your character, something like that. The Mars rover has AI. And so this is if you think about the Mars rover, this thing's tooling around on the planet Mars, on the surface of the planet Mars. And it's there for scientific research. But what should it be looking at, right? If the Mars rover had to call home, say, hey, I think I got something interesting, scientists, tell me what you think, that latency, right? We think latency to Salesforce is bad from the UK. Just try to Mars, would make it pretty much an untenable situation. So the Mars rover, they installed some AI in it where it can look at a rock. It comes, you know, it's rolling along and it sees a rock and it says, let me analyze that rock using my AI to determine if I need to do deeper analysis. And so now the messages coming back from the Mars rover aren't queries, but data and facts based on AI. Optical character recognition's been around for a long time, so I won't talk about that too much. Chess and Go, I think I've heard that Go is a much more complex game than chess. I've never played it, but recently a human was conquered by a machine. Voice recognition is an interesting subtopic of this whole thing. Mapping and route optimization. Google, when you do a search for a place and you say, give me the route, you'll see alternate routes. You'll see a best route, a guess at a best route, a prediction. Those are all AI. And then, of course, you know, the pod bay door operation is part of that. I don't think you can do an artificial intelligence talk without HAL 9000. So anyways, what's interesting about artificial intelligence is some of these things you look at and you go, that's kind of blasé application of AI. And as artificial intelligence matures and becomes more ubiquitous, what happens is this aspect of the way that we think about AI, which you know, you may or may not agree with me, but when I think of artificial intelligence, I also have this kind of like mystical, magical aspect to it, right? It's a machine that's doing what only humans could do before. And as it becomes more ubiquitous, that magic kind of wears off, right? So, you know, it's rare that you go to your Google Maps and you see alternate routes and you're like, whoa, AI is awesome. But now with Alexa, everybody's going like, wow, Alexa's awesome. How does she know? So that brings me to the Echo. Because natural language processing, you know, when I started reading about Siri and Echo and Cortana and all of these digital assistants that were voice activated, natural language processing jumped out at me as having a lot of things to do in a very short amount of time. And so these are some of the things, understanding the semantics. So this is the meaning of the words that you're sending, that you're giving to the device. Part of speech tagging and grammatical analysis is all about the structure of the sentence. You know, you can say things many different ways, but mean the same thing. And then, and also semantically, it's like English is a terrible language, right? Because there's so many words that sound the same but mean something different depending on context. The ability to answer questions, sentiment analysis is a combination of tone as well as the words within the sentences and where they live within the sentences, because you can have a negative word like worst and precede it with not the worst, and you know, how's that sentiment figured out, whether it's positive, negative, or neutral. And then the whole part about recognizing speech. It's a speech to text kind of thing. How does it distinguish speech from background noise? So this is all a bunch of AI stuff. And how many of you guys have played with Alexa? Great. Well, how many of you guys would like to play with Alexa? So writing skills for Alexa is pretty fun. Oops. Getting ahead of myself. Stop. That's what I wanted. They call that the 3-finger demo. So you take 3 fingers and switch. So this is, oh, you're not seeing the screen. Okay. Let me do it the old-fashioned way. There we go. So even if you don't have an echo, a dot, a tap, you can still begin experimenting with Alexa, and you do it on this site. So you just sign up for an Alexa account. This is tied to your account. I'm going to just refresh this. Control R doesn't work. And so this is a site. Alexa is actually a service run by Amazon that the Echo communicates with. And so anything that can communicate with that service can start to have Alexa-type characteristics, like a web page in this case. And so I'm going to try to demo this to prove a point. What is the airspeed velocity of an unladen sparrow? I hate Alexa demos. Can't hear it? Oh, for heaven's sakes. Where's my AV guy? Headphones, got it. Okay, it just switched. I got it this time, sorry. Let's try that again. What is the airspeed velocity of an unladen sparrow?
Unladen sparrow's airspeed velocity is 11 meters per second.
Is that what you guys are expecting? Let me try it again with a slight variation. What is the airspeed velocity of an unladen swallow?
That depends if it's an African or a European swallow.
All right. So we all recognize that as a Monty Python and Holy Grail reference. And you can continue that conversation with her, by the way. But all I did was change one word there. And it was able to actually, for some reason, if I wanted the sparrow velocity, I don't think I could get it from Alexa. But anyways, it processed and kind of determined, yeah, actually, he's probably not looking for that airspeed. He's looking for the quote. So anyways, fun with Alexa. There's a really fantastic Alexa fail, but it gets a little bit adult. This little kid, right? He's like, Alexa, play Hootie Dootie Dootie, you know, some music thing. And all of a sudden Alexa goes, I heard you wanted to order porn, and then it starts doing all these porn titles, and the parents are like, stop, Alexa, no, Alexa, stop. It's really hilarious. And with all the promise of AI, AI does fail once in a while. Okay. This is really weird that I'm on Slide Master. I don't want to be on that. Okay. So this is the part of the talk where I really want to talk about machine learning and try to give you an idea of what's involved with creating artificial intelligence. And so this is it, right? So this is a good representation of machine learning. Who can read this equation to me? You can read the full equation? I kind of figured you'd be the one. Do you know what it does by looking at it? No, well. Okay, so this is actually one of the simpler algorithms for processing and classifying data, a piece of data coming in. I can't read it. I don't know what all those symbols are. But I don't have to know how to read it, because data scientists can read this and create these. Data scientists are the new rocket scientists, right? And I think that if you have advice, as Peter Coffey was referring to anybody who's in school interested in technology, this is really an area that they should look at. I mean, Salesforce employs tens of data scientists, right? It's not just one or two, geniuses in the basement. We have whole teams via acquisition or hire. So what this is saying is, given the data on the left, look at the entirety of the data set on the right and tell me which piece of data it's closest to. In other words, what kind of classification it is, right? Is that pretty close? So that's like the sum of all the pieces. And so this data set, what's interesting about this particular function is the data sets used for machine learning need to be really big, really big, to have accurate results. And so this is why you need really complicated algorithms. And this, like I said, is kind of one of the more simplistic ones. But at the end of the day, we give a trained machine some data, and they give us what they think the data means. And I'll go into more detail on that. But before I do, I want to talk about learning in general, how people learn. So the way that we learn is pretty much we observe the environment around us. We observe things, and observation it can be just looking, but it can also be an in-depth study of a topic, right? We're observing how molecules behave and that kind of thing. And then we compare our observations to expectations, and if they match, it's great. If they don't, then we've learned something new, because we can categorize that as a new piece of information, and then we enrich our mental model, and then we keep doing that. So if you start with a very quiet mind, a very fresh mind, and you say, here's a ball, this round thing, and you look at it, observe it, and then you have nothing to compare it to, so it's fine. You have a mental model of one thing. And then somebody hands you a cube, and you go, this is another object. Does it look like a ball? Well, no, not quite. There's some differences. There's pointy edges and whatever. So then we're told, well, that's a cube. And so now you have a mental model of two things. And then that happens gazillions of times, and we're able to speak, interact, love, hate, make war, all of that kind of stuff. Machines operate in a very similar way. The assumption here is that we already have an environment, a world modeled for the machine. So this is this world is the data that the machine cares about, right? So there's different tasks. We've seen all the different AI tasks that are around today. Those have specific domain models, if you will. And when we feed input into that model, it evaluates its performance. And the way we evaluate the performance is, it's like, is that the right answer? for the question that I gave it, the data associated with that, was it the right answer? If not, if it is, it's fine, right? That's reinforcement, the model continues to work. If not, then we refine the parameters. And we don't refine the data to match our algorithm, we refine the algorithm to match the additional data. And then in that way, we're refining the model. Right, so it's very similar to how people learn. There's 4 core areas that you need to know about for machine learning: compression, classification, regression, and reinforcement. And so, again, you know, we need data lakes. That's actually what they call the data that our machine learning at Salesforce works against. You're not going to be working against all your lead data for lead scoring. You're going to be working against some processed version of that. So if you think about a lead, it can have hundreds of fields on a lead. And if I want to score a lead, see if it's more likely to close than another lead, I'm probably not looking at all 200 of those variables, but maybe 10 key indicators. And so if I had to process hundreds of fields on a record for each of the thousands and tens of thousands of records, that's going to cost me in performance, it's going to cost me in speed, and might be untenable across millions of records. And so we're going to compress that down by only paying attention to the data that makes sense, not the noise. And it's actually very similar to image compression, right? So there's zip and GIF and JPEG and PNG. And what those all try to do is make the file smaller without losing the meaningful data of the image, right? And they're pretty successful at that. So compression is a big part of that as well for machine learning. Classification, in my estimation, is kind of trying to understand what's important for developers to know, is one of the key concepts that you need to understand for machine learning. And it's really as simple as, is this input an X or a Y? Machine learning is a lot like the computers that are programmed to use machine learning. You know, at the very base level of computers, it's ones and zeros, right? On or off bits. And the same is true with machine learning. And so, you know, the ones and zeros get more complicated. You start bringing more inputs together, stringing data together. Machine learning is the same way in the classifications, right? So if I give it a picture of a cat, I want to know if it's a cat, yes or no. And so that's a classification. Classification is very close to categorization. Classification is kind of binary. Categorization is classification across more than 2 states, right? Regression is a little bit harder concept for me, but it's essentially you know, figuring out the relationships between the data, because it's not always a step change in state between pieces of data. If something is, if you're trying to make classify a value as a 0 or a 1, classify it as a discrete value, and it's somewhere between 0 and 0.4, there's a relationship there to how far away it is from 0.5, right? That makes it 0.4, that makes it a 0, in other words. And then reinforcement is primarily with mechanical AI, where, you know, you're driving the car down the car is driving itself down the road, and it makes a slight adjustment, and it says, am I still on the road? It says, yep, so that's positive reinforcement. If it makes an adjustment and says, am I still on the road? And it's, no, 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 that's negative reinforcement, which will cause a modification to the behavior. So those are the 4 key areas, but classification is the most important. And I think to illustrate this, I've borrowed a little bit. So a lot of this I learned from a gentleman who used to be at Salesforce, one of our early data scientists, Gary Flake. So I have to give him credit for a lot of these concepts. And what we're seeing is a set of data. Some are classified as red and some are classified as blue. So how do we teach our machine to figure out the classification for this? Oops, wrong way. So, we're trying to figure out a rule that we can apply across all data. And this is a simple rule that seems to work for the data, right? It's basically, I forget which axis is which, y equals n. So any piece of data that I am evaluating and trying to classify, if it's less than n, then it's a blue. If it's more than n, then it's a red. Is there any problems with this being so simple? Well, if a piece of data comes in that's up by the blue group and a little bit to the right, it may be misclassified as a red because this is just a very simple classification. So another way we could do this is maybe take X and Y into consideration. Any problems with this one? Seems to kind of favor finding blue stuff, right? Because it's so close to the red. And so classification really is about finding a boundary that maximizes the margin between the two classes. And so what that means is that we have, oh shit. Did you see that? Walked right off. So this distance and this distance should be the same. And the reason to try to do that is because we're trying to create a model that will be able to handle the next piece of data and predict where it belongs. And so if something lands near the line but on one side or the other, we can predict it. But we don't know where the next piece of data is going to land. This is a little more complicated one. I'll let you look at that for a sec. I don't know what y equals 10 means above the graph. And so you can see from this picture that a straight line isn't always going to make it for you, right? So we can create functions that create curves. But really what we're trying to do is find a rule that just separates two or more classes. And it's the or more part that really gets to me because, let's go back to our lead. This is basically one attribute that we're looking at. And a lead has 10, we decided that we're going to compare. And so now we're doing this in 10 dimensions. And so the math all of a sudden is like an order of 10 magnitude harder. There's a lot of machine learning systems that have like hundreds of dimensions. But these data scientists, these really smart guys who are like rocket scientists, are able to apply the math to be able to approximate and get orders of confidence around 97, 98%, which in some cases is way too inaccurate. In other cases, it's more than enough. What am I doing on time? I gotta go. Okay, so that's the end of like this really kind of theoretical based stuff. We provide sample data, we test it, and then we adjust. Right? So we just keep going around and around and around. But so now that you guys have that fundamental understanding, what is it Salesforce can do for you? Right? That's the big question. And wait for it, the big animated slide. Einstein is your data scientist, right? So, I'm sorry, my voice is starting to go. With Salesforce Einstein, what we're doing is we're taking all this machine learning that Salesforce has been looking at over the years. As a matter of fact, I've got a page here that's pretty interesting. And this is called SQUAD, Stanford Question Answering. Sorry. Drop out, then move. This is called SQUAD. And this is kind of a standard test for machine learning algorithms. And about 2 months ago, Salesforce team right here was at the top. And 2 months later, now they're down to like 4th, right? So there's so much activity going on here, but Salesforce is one of the leading companies that is doing research around optimizing these algorithms and creating amazing AI. So I thought that was pretty cool, actually. I'm like, Salesforce is doing that? So we want to take these machine learning and give you a smarter CRM, right? Make our core platform smarter, where you don't have to know all the details. So here's everywhere we're bringing Einstein to bear, where we've either brought Einstein to bear or will be. And the one at, it's Sales Cloud Commerce Community, but also the App Cloud Einstein. I'm a developer evangelist. I like the App Cloud. And so that's what we're going to talk about. The Einstein brand versus the Einstein, the platform. Einstein, the brand, is those pieces that are making the CRM clouds smarter, right? It's embedded. It's basically black box. We'll be providing some knobs and dials for admins to be able to adjust certain things, but pretty much no touchy. Einstein, the platform, on the other hand, is a way that we're giving developers so that they can create smart applications that take advantage of machine learning. Within the Salesforce ecosystem means that it's our stuff that it could be Heroku, it could be Salesforce Core, it doesn't matter, but it's provided by Salesforce. So what we give you with the platform is data movement. So this is the ability to import lots of data, to move data from your CRM objects into that data lake, export a lot of data. Scalability, we always want you to be able to do things at scale at Salesforce. And if you're looking at performance data, you're collecting lots and lots and lots of time-based data. And so data scalability is part of that. The ability to model, to retrain your models based on either data events or time frames is something that we handle for you. Security and trust, #1 value at Salesforce, of course. And then everything is going to be ultimately integratable with the other aspects of Salesforce, so from the platform to the various clouds. And then we'll do all the monitoring. Really, the end result is this, a production-ready system for taking advantage of intelligence in the applications that you're building on the platform. So then the question is, why do I care? I think Peter Coffey did a pretty good job of explaining why you should care as a developer, a technology person, about artificial intelligence at this point in time. Simply put, it's all over the place today. The second one is interesting because people are now expecting artificial intelligence, not the word, but the concept, right? Smarter apps. I expect Google Maps to give me 4 different routes based on my request. So the interaction assumptions are interesting. Machine learning is a key element I think we saw in voice recognition and natural language processing. As we are moving through this technological timeline, we're seeing fewer and fewer apps that rely on only keyboard or screen input and are more voice activated. And then IoT is putting so much data up in the cloud, and we need to be able to take advantage of it. We need to understand how to bring machine language to bear on that problem so that that knowledge is released and not locked up. With that, I'm going to talk about one aspect of the Einstein platform called our Predictive Vision Service. This is something that you can go and sign up for today, right? So this is the very practical part of the presentation. And we do two things with this. One, we give you prepared data sets. So we have data sets for different things like food, automobiles. We have some ones around different kinds of buildings. And so you can use those data sets and snap your lunch and send it to the Predictive Vision Service, and it'll tell you whether it's a burger or a plate of pasta or whatever. But more interestingly, you can train your own data sets for your own purposes. And it's after seeing all of that machine learning stuff in the beginning, I hope that when I show you how to do this, you'll go, okay, fine. I understand the basics, and now I know how to do it. I don't need to go back to school and be a data scientist. So to demonstrate this, I've created my own facial recognition service. It's called JKS, and what I've done is I've put in some data, pictures of three of my favorite people in the UK, Jenny Bamber, Carrie Townsend, and Sean Holmes. And what we're going to do is take yet a different picture and ask it to tell us which one of those people it is. So, pardon me. Okay, so the MetaMind API is a simple REST API, and it requires you to kind of do three things. One, to create a data set. That just means creating and naming a data set and defining the labels or classifications that are within that data set. The second thing is to train the data set, and I'll show you how easy that is. And the third thing is to go ahead and use the data set, query the data set. So it starts with a simple client. By the way, this is all up on GitHub, and you can get access to it from the metamind.io site. We need an API token, and I have to actually refresh that right now, so pardon my terminal. Oop, try it again. Looks like I'm almost out of time. Okay, let me grab that and then put this in my client. Okay, now she's alive. Okay, so this is just setting up a simple client. So create and train. So it all happens within this section here, and I'm creating my data set using this post, right? This goes to my data set endpoint on MetaMind. After the data set is created, what I'm going to do is I'm going to go to this folder called Peeps. And I have a folder for each of the people that I am training the data set on. And it's going to walk through those folders and upload those to MetaMind with the label associated with the folder name. And so that's what's happening in here. This is all for uploading. And then finally, I get down to the train method, and this is going to train the data set. And to do that, you basically send this post data to the train URI at MetaMind with the appropriate data set ID and name. You've already uploaded the pictures, and it just creates your pretty cool model. So let's go ahead and do that. Now that I've refreshed my token, over here I can... Oh, by the way, this is just a simple Node app running locally on my machine. I could have put a web interface and put it up on Heroku and all that kind of stuff. But I didn't. So I'm going to call createandtrain.js, right? So that's this file. And so what's going to happen is it's now uploading the data. It uploaded 56 images, and now it's training. So MetaMind is churning and creating this model and figuring out the proper algorithm. I can then monitor that training. So it takes about, I don't know, a couple of minutes, a little under a minute, I think, for this to happen. But basically, it's setting up those classifiers for me. It's creating the data model that it can then use to classify. Hope this finishes soon, because we're almost out of time. And so let me go ahead and show you some of the photos that I used, in this case, Jenny. So these are just faces that I've chosen off of Facebook. I've cropped some down. They're various angles. This is a tiny data set for this kind of thing. You really want thousands of pictures if you're going to try to do something like this. Let's try that again. Succeeded. Okay, right. So now that we've succeeded, what I'm going to do is go ahead and drop a picture in here. So I'm going to say the test class, by the way, is who is this? And it very simply just sends the data up and then reports back. So node, who is this? And then we'll just drag her into there and hit return. Thank you. I'm learning how to use these computer things. It takes a while. So everybody see that okay? Well, let's make this a little bit more clear. Let's ask Serena. Well, actually, let's see. I have to check my code. Yeah, everything looks good.
So, Dave, I put a 94.5 for 177% confidence level that the picture is of Jenny.
So the point here is that you can see three different confidence levels, right? And this one is Jenny, but it's only Jenny because my application defined 94% as being sufficient confidence level, right? Let's try this one here. I got about a minute left, I think. Good old Sean.
So, Dave, I put a
So
99.84938% confidence level that
That's
the
even
picture is
better.
of Sean.
Let's do one other one. We'll try this one. I spent so much time goofing around with pictures.
That does not appear to be a Sean, a Kerry, or a Jenny.
So even though Jenny's at the top with 77%, you can't just go like whatever the first one is matches, right? So it's important to understand your data, understand what is an acceptable level of confidence, all of those kind of things. I'm going to do one last one. You wouldn't believe how stressful it is typing under a deadline. Let's try this guy. Anybody recognize him? I think that's Beavis.
So, Dave, I put a
Oh,
99.99939% confidence
Clearly
level
it's
that
not
the picture
Sean,
is of
but it's
Sean.
close enough. And maybe we need to add more data and retrain our model. So yeah, so it's kind of fun playing around with that, but hopefully that gives you an idea of what you can do today with MetaMind or Predictive Vision Services. There's a couple of links here. They're pretty easy to find. Basically, we've got two things that we can put in your hands today. There's the Vision Services, and then there's the Prediction.io, which is more about recommendations and sentiment and things like that. So please feel free to go there and screw around with that stuff. It's totally free. Waiting for one picture. There you go. And that's it. Thank you very much.